Good afternoon, everyone, and thanks very much for having me today. I'm going to attempt a brief effort at Spanish here, so bear with me.
I'm sorry,
This,
Ayesha, your volume is very low. If you could
oh,
raise your volume, please.
how about now?
Yes, that's better.
Okay. Desafortunadamente, el español que estoy
Unfortunately, the Spanish I'm speaking right now is the last words I will make in Spanish. For the better words, you will bear with me my English.
use of PXRF in assessing the porphyry potential of intrusive rocks. If you are a geoscientist, you've probably used a portable XRF device or dealt with PXRF data at some point in your life. If not, it's a rapid analysis tool that can collect ppm level concentration data for a pretty large suite of elements. In the exploration and mining sector, PXRFs are commonly used on drill hole pulps for domaining of alteration, mineralization, and rock type. Pulps represent a homogeneous sample medium, and this makes them really conducive to generating reliable, reproducible PXRF results. But the PXRF is also used in earlier stage or greenfields exploration. But I would say that largely this is to support mineral ID or grade estimates of potentially mineralized samples. Less commonly is the PXRF used to collect useful whole rock geochemical data, particularly on medium to coarse-grained rocks. This reticence is rightfully based on concerns over the compositional variability or heterogeneity across a hand sample, depending on grain size or texture. What I'll present today is a PXRF workflow that can be undertaken in the field or after a field campaign to get cheap, reliable, and reproducible porphyry fertility information, specifically for intact rocks. So just like you see on the graph shown here. So here's the plan for the remainder of the presentation. I'll first provide some background on a few commonly used porphyry fertility diagrams. Next, I'll walk you through the workflow that was used to collect and calibrate PXRF data, specifically for intact rocks. I'll also discuss sources of variability from PXRF spot analyses on rock samples. And finally, I'll finish off with a couple of case studies to demonstrate how the results stack up to more conventional laboratory-based analyses. First, a note on copper prospectivity diagrams. Strontium over yttrium has been established quite well as a proxy for magmatic water content. Water content is important, as we know, in porphyry deposits because porphyries are very large, generally low-grade, magmatic hydrothermal systems, and they require large volumes of fluid to mineralize large volumes of rock. The graph that's shown here demonstrates that in normal dry arc magmas, those are the gray dots, strontium over yttrium decreases with advancing fractionation. And this is largely due to the crystallization of plagioclase. In hydrous or wet magmas, though, the combined processes of plagioclase suppression and early hornblende fractionation work to increase the strontium and decrease the yttrium during fractionation. So this means that ore-forming hydrous intrusions have overall higher strontium over yttrium than barren suites. This knowledge is not new. It was developed using whole rock laboratory data and has been quite well adopted by industry as an exploration tool. Perhaps less well established is the behavior of manganese. Back in the 1980s, Baldwin and Pierce identified an empirical relationship between low manganese and porphyry ore-forming intrusions. The data that's shown here further supports this empirical observation. So with advancing fractionation, the manganese content of a dry melt stays relatively constant, as you can see by those gray dots, whereas it decreases in a hydrous melt. This is likely also controlled in a similar way to yttrium by early hornblende fractionation. Now, it's just important to note that both of these exploration or prospectivity diagrams are typically informed by whole rock commercial laboratory data collected on intermediate to felsic intrusive rocks. But we wanted to know, can we use the PXRF to collect much cheaper, but still reliable, robust, and reproducible porphyry fertility data? Luckily, strontium, yttrium, and manganese are readily collected by most PXRF units. So what we did was recombine the axes of the two fertility diagrams that I just showed into one diagram, strontium over yttrium versus strontium over manganese, losing silica. We got rid of silica for a few reasons here. So first, on both fertility diagrams, silica is used as a proxy for the degree of fractionation. But if we take a minute to think about our exploration reality, samples collected in the field do not typically represent a genetically related suite of rocks forming along a fractionation trend. Instead, samples are essentially point data, and this makes silica less important. The silica content of a rock is also highly variable, particularly if we think in terms of the field of view of a portable XRF, which is on the millimeter to the less than centimeter scale. And lastly, if we're honest with ourselves, older PXRF models really collected terrible silicon data. The newer models do a much better job of this, though. So next, I'll go through the steps that we took to collect and calibrate our data. I don't want to get hung up here on the ins and outs of different PXRF models. The detection limits, precision, and accuracy of different elements will vary between different PXRF models, but also likely between instruments of the same model. So it's more important to set up a rigorous QA/QC and calibration workflow for each instrument. For our study, we collected data using an Olympus Vanta M series PXRF with a 50 kilovolt rhodium tube and using geochem mode. The first step of the data collection workflow is to analyze a series of matrix matched standards and blank material. By matrix matched, I mean that you want a suite of standards that reflect the rock types and geochemical compositions of the samples you're analyzing. But also, you want to have a broad range in concentrations of your elements of interest that allow you to generate robust calibration curves. In our case, that would mean standards with low, moderate, and high concentrations of strontium, yttrium, and manganese, so that we can be confident of our calibrations across a range of data values. So once you've collected data on each of your standards, you visually inspect the data just on the PXRF screen to ensure that values are within an acceptable range. And this acceptable range would have been predetermined in a designated data collection campaign for QA/QC material prior to heading in the field. The next step is to collect spot analyses on your rock samples, along with a recommended 1 in 20 QA/QC samples. I just want to spend a little bit of time talking about this step in particular of collecting spot analyses. So I'll come back to this workflow in a moment. On each of the rock samples, we collected 3 spot analyses, avoiding areas of veining and alteration. So why is 3 the magic number, you might ask? Well, we wanted more than one analysis in order to represent the natural variability or the intrinsic heterogeneity in rocks. And this is a function of mineral distribution, texture, and grain size. Collecting multiple PXRF spots is not really necessary when you're using a sample medium like pulps because the rock has been pulverized and homogenized. So no matter what part of the pulp is analyzed, you're likely to get the same answer. But intact intrusive rocks are not homogeneous specimens. And as you can see here, if we collect 3 different spots on the same sample, we're likely to get 3 different geochemical compositions. So the problem only gets worse the coarser the grain size. So the question follows, is the variability between multiple spots on a given sample acceptable to provide us with useful fertility information. Shown here are strontium over yttrium results from 50 spot analyses collected on each of the rock samples shown, fine, medium, and coarse grained. And what we see is that absolutely there is variability between analyses, and you can see this by shifts on the y-axis. And certainly the coarse grain sample on the right is showing a much wider range of values compared to other grain sizes. But still, from a practical point of view, if we were to pick 3 analyses at random from each of these samples, we would expect to represent the sample population quite well. Although it would be lovely to collect 50 analyses on every sample, this is, of course, neither time nor cost effective. If we bring this data back of the fertility diagram, just back into data space, we can see that the natural variability between spot analyses does not inhibit samples from being classified as prospective or unprospective. So our data is fit for purpose. As with any quantitative analytical technique, there is an associated analytical error. The graph in the middle here highlights this relationship between element concentration and associated analytical error. At low strontium concentrations, approaching the detection limit, analytical error is high compared to the error at higher strontium concentrations. And this is because the detector in the PXRF is not receiving adequate signal to estimate concentration accurately. Note here, though, on the y-axis of that graph for strontium that we're talking about less than 1% error. This is really, really low, good data. The analytical error for manganese and yttrium, not shown here, is higher. It's up to 30%. And this number may seem really high to you, but again, let's bring it back to the fertility diagram on the right. What you can see is that the analytical error bars show that we can still confidently distinguish between different samples and different fertility responses, even with analytical uncertainty. So again, our data is fit for purpose. All right, so we're back to the workflow. The next few steps are absolutely crucial to generating good data, but I'm not going to dwell on them because there have been many studies published on the importance of validating QA/QC samples and generating calibration curves. So definitely email me if you're looking for specific references. Suffice it to say that standard and blank analyses from the data collection campaign need to be evaluated to ensure they pass previously determined acceptable thresholds. Once passed, the standards can be used to generate calibration curves. These calibration curves relate PXRF data from your standards to conventional laboratory data on the same standards. And the final step is to apply the equations from the calibration curves to the PXRF data in order to generate laboratory normalized or calibrated quantitative PXRF data. Before moving on to the case studies, I just want to touch briefly on the potential effects of alteration on porphyry fertility signatures. The formation or destruction of any mineral that contains strontium, yttrium, or manganese will inevitably affect where a sample plots on our fertility diagram. As an example, on the left is a rock sample with a thin epidote vein enveloped by an epidote albite vein halo. And this is typical propylitic style alteration in the porphyry environment. What we can see from micro XRF element maps of the same sample is that strontium is concentrated in the epidote vein and epidote in the vein halo. Conversely, manganese has been destroyed in the vein halo relative to least altered areas. Another example is shown here. A PXRF spot analysis of the least altered side of this sample returned lower strontium, but similar manganese and yttrium values than altered parts of the rock. If we plot these two analyses on our fertility diagram, the least altered analysis falls in the barren domain and the altered analysis plots in the fertile domain, resulting in a weak false positive. So just take this as a cautionary note to always attempt to analyze the least altered parts of rock samples. And this example really highlights a strength or added benefit of using the PXRF here, which is the ability to niche sample centimeter wide least altered domains of an altered or veined rock. All right, on to the case studies here, and I've got two. Our first area is the Yarrington district in Nevada, host to the Ann Mason porphyry copper deposit, as well as the Yarrington, MacArthur, and Bear deposits. Post-mineralization basin and range faults at Yarrington have tilted parts of the district up to 90 degrees so that cross sections through porphyry systems are exposed at surface. And this is reflected on the map here, where the bottom of the screen represents the deep roots of the porphyry, and the top of the screen represents the shallow roof above the porphyry. The geometry here has really facilitated the study of paragenetic relationships between different intrusive suites and mineralization, and this has been supported by absolute dating methods. So this is all to say that at Yarrington, we can be very confident of our classification of pre, syn, and post-mineralization rocks. What does our PXRF fertility data tell us? Well, on this graph, each data point represents an average of the three analyses that we collected on the sample, where the error bars represent the standard deviation between those three analyses. And what we see is that pre and syn mineralization intrusions, these are from the fertile Yarrington batholith, have high strontium over yttrium and strontium over manganese values, with the syn mineralization intrusions reaching the highest fertility indicator values. Conversely, the post-mineralization intrusions have lower strontium over yttrium and strontium over manganese, and these intrusions are related to a different batholith, likely tapping a different midcrustal reservoir. This slide really highlights the excellent correlation between PXRF and whole rock data from the same samples. So what you can see is that both absolute values and patterns, relative patterns between pre-syn and post-mineralization intrusions are preserved in the PXRF dataset compared to the whole rock dataset. The Cowl Deposits, this is the second case study area. So the Cowl Porphyry and Epithermal District is located about 100 kilometers west of Cadia in New South Wales, Australia. And Cowl is host to a suite of epithermal gold and porphyry copper gold deposits, and those are shown on the map here by the different colored rock and hammer symbols. So formation of these deposits is associated with intrusions of the Ordovician Cowl igneous complex, part of the Macquarie Arc, and those intrusions are shown as different shades of pink on the map. Again, what do we see with our PXRF prospectivity data? We see that pre and post mineralization intrusions have low strontium over yttrium and low strontium over manganese values, and syn mineralization intrusions have high strontium over yttrium and strontium over manganese. Similar to the Yarrington data set, we see the same patterns in our PXRF data shown on the left as the commercial laboratory data on the right. And of course, these were again collected on the same samples. All right, so to wrap up, hopefully I've demonstrated today that using a robust data collection workflow, PXRF spot analyses on intact rocks can be used to inform fertility diagrams. And there are a lot of benefits to using the PXRF for this purpose. Data from more samples can be collected with little additional cost, meaning that we have much better population statistics to base decisions on, and we can characterize entire intrusive suites. Performing analyses on intact rocks means no sample preparation, no crushing, no sieving, and this saves time and money in the field. Using the PXRF means that we are able to target least altered parts of a rock, whereas it can be difficult to find least altered hand specimens for whole rock analysis in altered porphyry environments. And finally, and most importantly, this workflow has the potential to be applied in the field, allowing geologists to make data-driven decisions that inform sampling or mapping campaigns on the go. Thanks very much.